Dr. Sundar, shall we start? Dr. Sundarvel?
Yeah, yes, sir, we can start. So,
Okay.
very good afternoon to all. Now, the session 2 will start. May I now request Dr. Prabhakaran to share the session 2.
Good afternoon, everyone. Indeed, it's a great pleasure to meet you all after having a good lunch. I do hope that you all had a good lunch. For afternoon session, I will introduce Professor Dr. Sundar Duri, who is from University of Goa University. Professor did his PhD and a master's in Goa University, and he was the University Research UGC Fellow and DAD Fellow, and also he was working with Professor Won Won Nam at Eva Women's University, South Korea, and currently he is a professor of Goa University. As far as for his credentials, Dr. Sundar Duri had four projects. Among them, DST Serb UGC as well as DST Nano Mission project and DST CSIR project. He had published more than 35, of course, 40 papers with the citation of 662, having the citation index H index of 16 with the I-10 index of 21. He has also published a number of research articles in Journal of American Chemical Society, Anglo Andy, like Dr. Sangaralingam, what in the morning session we had. And he is a member of a number of professional bodies. Within the few words, I do invite Professor Dr. Sundar N. Duri to take over the session to share his expertises with the participant. Thank you very much.
Yeah, am I audible to you?
Yes, you are.
Yeah. Thank you very much, Dr. Mohan. I'm glad to hear your words. Thank you very much. Yeah. I'll just start my presentation sharing with you. Just tell me whether it is visible to you.
Just, Doctor, you can just adjust your camera.
Okay.
Your face,
Now it is okay?
Yeah, now it is okay. Yeah.
What I will do while presentation, I will put off my camera because of some bandwidth and other things here. So I'll put off my camera. Is it okay?
Yeah. Okay. You can.
Okay. Once again, thank you very much, Dr. Mohan. Yeah. Am I audible to you, Dr. Sundaravel?
Yeah, you are audible.
Yeah,
you are audible.
Yeah. First of all, I must thank the organizers for giving me an opportunity to speak on some work what I'm doing at Goa University, or share my experience with the students as well as the faculty members across India and other places. So I'm very glad to be a part of this webinar international seminar series, and I should or I must congratulate the entire team of the Department of Chemistry, right, for organizing such a very important event. I mean the symposium. Yeah, I'm very glad for that. And as I given the title, this is my title, the heme and non-heme ligand based transition metal compounds in organic oxidations, and there are other applications. So some few applications I'm going to speak. Okay, and I'm going to tell something what I'm going to do, we are doing at Goa University, as well as my past experiences. So before going to my actual presentation, just I want to give a glimpse of Goa. So Goa, I mean Goa, all of you know, is a tourist destination. So Goa is basically is known in India and other places as a tourist spot, and for enjoying sun, sand, and fun. Okay, so that is what all about Goa is known. So Goa is having a lot of biodiversity, a beautiful. No, we are situated. Goa state is situated in Western Ghats. We have a beautiful greenery. We have a, you can see here, we have a beautiful temples, churches, mosque, and all everything we have, whatever is there, and it's very peaceful state. So I am sure when you come to Goa, you will enjoy your sometimes sometime in Goa whenever you come here. So do contact us, no problem. So besides this, so besides the enjoying in Goa, right, whether some science and other things is taking place or whether education is taking place in Goa, so I would say yes, very much. Goa is very much no, doing well in terms of science and technology and other fields of education. Yeah. So Goa University is the only state university in Goa, only state university, and besides we have the NIT Goa and IIT Goa, which are just coming up. Right. So since only state university of Goa, so it caters the needs of all the students in Goa from remote areas of remote villages as well as the remote parts. So this is my department. So now it is named as the School of Chemical Sciences very recently. And you can see here this building. So this I will check it. Oh, I can use some arrow or ball pen, something like that. Okay, I'll use this arrow. This is our main building. This is only a School of Chemical Sciences building. So left hand side you would see some the Life Sciences building is also there. So it's a big building with the two wings. So anytime you visit, you are welcome to our School of Chemical Sciences. We have about 31 faculty members, and we are admitting 100 students for first year. So also 100 students for second year MSc, and we have around 50 students, PhD students. Yeah, so that much I mean the new faculty members are recently joined in 2020. Almost 20-25 people have been appointed. The rest of the faculty members are all the senior professors. Yeah, so we have some infrastructure, very good infrastructure at Goa University. Since you can see the new building, so this was given to us by state government of Goa. So we have some good infrastructure for the benefit of students, so they can do research, they can do other activities as such. So these are some of our what you call the instrumentation facilities what we have. Just I'm sharing some of them. So we have a NMR spectrophotometer and many of the instruments which are basically required for nanomaterials, etc. So we have those things. Recently we bought a single crystal diffractometer, so wherein we can do low temperature studies also. So that we also purchased recently. So some of the equipments you can see here, they are also there photoluminescence and some fixed bed catalytic reactor, high pressure part. So all those things are there. So many of our faculty members, they have their own projects, as well as we have a DST FEAST program and UGC SAF programs going on. So therefore we because of this particular support, we were able to establish our department with lot of infrastructure as far as research is concerned. So this is just some glimpse of my department. I just wanted to share because at the end I'm not sure I will be able to get time to share these photographs with you. Yeah. So coming back to my the title of the talk. So this is the title of my talk. So heme and non-heme ligands based transition metal compounds. So I basically say transition metal compounds, which includes the high valent metal oxygen intermediates as well as the other catalysts what we have used here for doing organic reactions such as the CH activation, hydride transfer reactions, oxygen transfer reactions like that. And we have also, in addition to these organic reactions, we have also done some other applications. So those also I am going to share with you. So when we say the uh, biological applications of these metal compounds, so all of us we are very well known that no monooxygenase enzymes are popular in biology, right? So we call them heme and non-heme system. So basically we have a cytochrome P450 wherein we have a, heme system because we call heme because it contains a porphyrin, and in biology also we have a non-heme systems wherein we don't have a porphyrin systems, right? So to give two examples of monooxygenase, they are here, and basically what they do is they do the oxidation reactions. So they convert the substrate into a product, okay, and the product will have oxygen in it. So that is what they do in our biology. So mimicking this particular compounds is a long back, somewhere 40 years back or 4 decades back. It was not so easy, right? But people were doing those days in 1980s. People used to do it. So there is a nice paper, uh, nice paper on this cytochrome P450, wherein they had given some sort of a proposal that this iron goes into iron 4 oxygen species and iron 5 oxygen species, like that. So those days they had proposed, but in reality you will find that those things are being now proved by experiments as well as by some evidences. So this is a catalytic cycles which all of us probably we are very familiar with it. So this is very important. Most of the standard textbooks now sorry, most of the standard books is incorporating this particular cytochrome P450. So once upon a time, this as I said, 40 years back or 4 decades back. So once upon a time, the people used to just propose certain things, but now everything is. I mean, the people have given the evidences for this. Uh, this intermediates in the catalytic cycle of cytochrome P450. So you can see the resting site. So resting site something like it has a iron 2, then in the presence of a substrate, so it takes up the electron, goes to iron plus 2. So you can see the cytochrome, you have sulfur bonded in one side, that is a fifth side, and the sixth side is vacant. So you can see here sometimes so oxygen is there, so it will form the superoxo species. Okay, still the oxidation of RH, that is organic substrate has not taken place. Then further, what happens? You see, it takes up one more electron, goes to peroxo intermediate, and in the presence of a protonic solvent, so what it happens? It goes to hydroperoxo here, and then there is a homolytic cleavage to form sort of a what you call the so compound one. We call iron 4 oxo radical species, and this particular species actually is doing the oxidation. Okay, so you can see here. So from here plus 3 to plus 2 to plus 3 again, then go to your peroxo species, hydroperoxo species, and then go to pi radical cation. So here, as Dr. Shankar said, probably here the potential is so oxidation potential is so high that it is able to oxidize the RH into a product containing oxygen. So you can see, and then it goes finally back to yeah. So this is a simple catalytic cycle of cytochrome P450, and based on this, actually, based on initial what you call the literature available, people started doing mimicking this model, and then uh, by then over the 1.5 decade, people are actually successful in doing lot of chemistry in this area. So when we say a chemical, I mean modeling of things, so you will notice that I mean a lot of things are being done with the model compound. So this is one of the compound which was being used. This is iron TMPCl, very popular, and with this it was shown that it can form your pi radical cation, etc. So a lot of chemistry is being already what you call the developed. So I'm not going to go into detail. So this is very important for that. And when I say the model compounds, so these model compounds, they are able to perform the reactions what are being observed in the biology, right? So you can see here, so many reactions are being done by these model synthetic compounds, and they were for, I mean, in 19, you can see 1981, the Gross et al. They just first gave some sort of a proposal saying that iron 4 oxygen species exist with the in cytochrome P450. So this is done with the model compounds. So you can imagine a lot of hardship those people had taken to come to the arrival, saying that no, this iron plus 4 oxygen species or plus 5 oxygen species exist in the biological systems. So later, when a lot of heme systems were already taken into account, lot of things were done. Okay, many reactions were done, oxidation reactions, where several substances were tested. Okay, the products were very well characterized by different techniques. Okay, and then after doing a lot of chemistry, so people started working on a non-heme system, because as I said, non-heme systems are also very important systems, right? And therefore no over the period of time, large amount of compounds which are called as non-heme iron compounds or some other manganese compounds, as Dr. Sankar said, right, have been already no became model compounds. So to give an example of some compounds, like here what we have, iron TPA compound. So you have a this compound again, you see this, you have a non-heme ligand, right? So four nitrogens are there. Then you have one astronitrile coordinated nitrogen. This nitrogen ball is a blue color, that is nitrogen. And then you have oxo group here, oxygen, right? And then this another pentadental ligand, N4 py. So again, the iron 4 oxo intermediate was very well characterized. And then very popular compound of iron 4 oxygen species is with the TMC ligand, that is tetramethylated cyclum. Okay, tetramethylated cyclum. So that particular compound actually gave a lot of no lot of compound, in the sense that the crystal structure of this particular intermediate is known, right? So NAM group, they actually report the crystal structure of this compound. And how it was studied? It was studied, I mean, the intermediate is forming or not. It was studied by simple UV visible spectrophotometer. So one need not worry about the other equipments to characterize initially. But what is required initially is one simple spectrophotometer. So for example, here you can see. So this was the intermediate species generated. So they started with iron plus 2 TMC complex. So you can see a red color spectrum is iron plus 2, and they use oxidant, that is iodosyl benzene. Okay, of course this particular compound also can be generated in air dioxygen activation. So what that happens is you can see a red color spectrum goes to blue color spectrum, right? And then finally here the absorbance is of the iron 4 oxo species is achieved. The species becomes very stable. Okay, it is so stable that it can be, I mean, it can be grown into a single crystals. And that is what NAM group did, Professor NAM group did. And they first published this crystal structure along with the reactivity of this iron 4 oxo species in Science 2003, right? So now you can see here, so this compound what just now I shown here, so you can see here, so again it's a sort of a planar ligand, and then you have the oxygen atom trans to this actual ligand. Okay, or I can say the actual ligands are trans to this oxygen ligand. So whatever, so oxygen is here which is coming from your oxidant, and then you can tune this particular, you can tune the reactivity of this compound by changing the actual ligand. For example, acetonitrile. So I can put some other ligand like trifluoroacetate. I can put acetate or some azide, etc. So one can tune the reactivity of this iron 4 oxygen intermediate, and then one can observe a different sort of a reactivities. So that is what I'm going to just tell you in next next slide. So this was done already. I mean, Professor Nam with our Professor Shastri already did actual ligand effect long back, somewhere in 2009 they published 7 they published PNS paper with actual ligand. Of course, lot of work was already initiated before that, right? So you can see also actual ligand effect when you do the change the ligand. So moment you change the ligand, so you can also trace those changes by using a spectroscopy, UV visible spectra, right? So you can see here, so initial black color, something like that, acetonitrile. Then you have some NCS ligand, so you get this color. You can see here there is a shift in the near UV region. And then you have one more ligand, the more electron donating ligand like azide. So you get another kind of spectrum. So change in spectrum also can be observed by UV visible spectroscopy. Of course, the crystal structure for these are not known, but they are very well characterized by ESI mass or HRMS or many other techniques. So there is no question that they exist in solution or not. So they are very much exist. So therefore, they have been no, they have been again and again investigated in different sort of works. So later in 2005, also one more crystal structure of iron 4 oxo species was reported by Nam and co-workers, Professor Nam and co-workers. But of course, this time not the what you call the not the nitrogen group or astronitrile ligand actual to the trans to oxygen atom, but this time you have a sulfur trans to the oxygen atom. And it was more fascinating because in cytochrome P450, just now I showed the structure and the metal active side of that. So you will notice that in cytochrome P450, the cysteine sulfur is coordinating to iron, right? So in that sense, it became very popular those days, and of course the reactivity, other things were very good, and that work again was published in Science by Nam and co-authors. So taking some sort of a what you call taking sort of a some sort of a motivation from this work, right? So in 2008, somewhere 2006, 2006, I joined Professor Nam's group at Center for Biomimicry Studies in Seoul, where Dr. Sundaravil and my colleague Dr. Sankar also worked, right? So in fact, Professor Nam introduced me to this particular chemistry, and that is how no, that is how we could do some good chemistry over there those days. So when I joined there in 2000 somewhere six, Professor Nam and of course our Professor Shastri, they did lot of work on this axial ligand effect, and they published a good papers those days, right? But however, my work was not again to work on the iron, but I thought I will do something else. So you can see here. So here, when you say iron, iron was published by in 2007 in the PNS journal. So what we thought, what happens when you replace this X? Okay, and what happens no replace this X with different ligands, and when what happens when iron is replaced by some other metal? So we thought that the best candidate would be the same metal which belongs to the same group, like ruthenium. So in that sense, we had chosen this ruthenium case, and that is what we did. So in iron, what was observed was that the substitution of acetonitrile with variety of other anionic ligands like trifluoroacetate, azide, or for example SI, thiolate, made it possible to demonstrate that the reactivity of iron 4 oxo species uh, is significantly affected. Okay, significantly affected in such a way that one can monitor it kinetic, I mean spectroscopy, or by some other method. So it was affected a lot by this action ligand, and that depends on the type of actually no that depends either in the CH activation and oxygen transport reactions. Those reaction actually the rates and other things were altogether different by changing this X ligand. So that was that was actually studied, and what was observed in the iron case was that so while electron donating axial ligands diminish the oxidative reactivity of this iron oxo species, especially towards the substrate like triphenyl phosphine, and the reactivity pattern was something like acetonitrile was more reacting that trifluoroacetate than the azide and then the thiolate. Okay, and they enhanced the reactivity of this oxo species in hydrogen atom extraction, and that reactivity was a little bit different. The trend was opposite. So what was observed in hydrogen atom abstraction was that the thiolate substrate, I mean the thiolate axial ligand oxo species was reacting much more faster compared to the acetonitrile. Okay, so the trend was different. So we wanted to know what happens when you change something like you have a when you change the to ruthenium. So that is the intention uh, of, of of that project those days, and then I was given that project. So when I did that, so initially I find the preparation of ruthenium oxo species itself was very difficult. It is not like iron species. Ruthenium compounds. Those who have worked on ruthenium, they will know that how difficult to prepare ruthenium compounds is. But of course, this ruthenium oxo species, the initially was prepared by Chiming Che group, and they did lot of work in 1980s. And when you compare the stability of ruthenium oxo species with iron spore species, ruthenium oxo compounds are very stable room temperature. Okay, so one can get the single crystals for many of these X. I mean X you can change it with acetonitrile or uh, trifluoroacetate, azide or NCS, anything you do. So most of these solutions is to give a crystal single crystal. So I mean you can make out that these compounds were very stable. Okay, so these compounds were very stable, but only initial things were quite difficult to prepare. So for example, you can see here, so preparation was actually started from ruthenium 3 compounds. So this you can see here, so TMC was added to ruthenium trichloride, which is actually a potassium pentachlororuthenate compound, and then what we get is ruthenium 3 compound, we get it. So from that ruthenium 3 compound we have to prepare a ruthenium dioxo species. So you can see here this ruthenium dioxo species, which is in 6 oxidation. Ruthenium is in 6 oxidation state, and from this ruthenium 6 oxidation state species and then other compounds were prepared. So that other ruthenium 4-oxo species, astronitrile coordinated, and all those species were prepared. So this initially we did not go because the structures and some of those compounds were reported. We did not go into much details about their characterization, but we characterized that in solution. So all the compounds were characterized by USI mass and all those things, and then you can see a beautiful UV spectra tells that they have a different spectra. Okay, so all X ligands you can see here they were replaced. They were replaced, and then you can different kind of no bands you get in the UV region. So coming back to the reactivity of this compound, so then we tested the reactivity whether it is similar to iron oxo species or whether it is different. So when we did that, actually, of course, the reactivity when we did, you can see here. So this is one reaction. This is triphenyl phosphine reaction. So around 440 nanometers, you have a ruthenium 4-oxo species. On addition of a substrate, what happens? The species slowly decays. We have a time trace. We obtain all the second order rate constants, etc. Right? So we use and then we compared it. Then when we compared with different ligands. So for example, you can see here the red color triangles. This red color triangles was nothing but actually it is azide. Okay, so azide and some NCOs, etc. And then you have a two. So this red color triangles that line what you say, that is azide and NCOs or NCO ligand, they are not showing any reactivity, and therefore you don't have any rate here. But what we observed was that with these two ligands, the acetonitrile and trifluoroacetate, they were showing a reactivity. Okay, these are actually from which the first order, no, you can see first order rate constants are plotted against their concentration. So we could get the second order rate constants, and we can easily make out that acetonitrile is when X is acetonitrile, it is much faster than your trifluoroacetate, and then further azide and NCO they are not reacting. Okay, so that pattern was observed in the oxygen transfer reaction. Now what happens when we have a CH activation reaction, that is hydrogen atoms transfer reaction? So whether the pattern is same or whether the pattern is different. So fortunately what happens is that, so in iron case, as I said to you, the pattern was you can see here the oxygen here this particular left hand side picture, the oxygen transfer and the hydrogen atom abstraction, these two reactions are altogether different. They follow a different trend in terms of X ligands by changing this X ligand. But when you had a ruthenium case, nothing happens. The reactivities were of the same. I mean, they were going in the same direction. The trends were same. So that is acetonitrile and azide were reacting in the same way, unlike your iron case, right? So of course, this experimental data was supported by the DFT calculations. We showed that in iron case, the both the state, that is your triplet state and the quintet state are accessible for the reactivity, but in the case of ruthenium, only the triplet state is accessible for reactivity, and the quintet state is far away from the triplet state. So in other words, the energy gap is so high that it's not accessible. So with that particular result, DFT result, this work was published in the Angewandti Chemistry in 2008. So that was really an interesting work. I mean, we could get in ruthenium chemistry. So then what happens is that, so I slightly shifted, since ruthenium, as I said to you, compounds were difficult to prepare. I thought, I mean, I will waste my time on ruthenium, and I thought I will change to iron. So again, I came to iron chemistry, iron oxo species, and I noticed in the literature those days that, okay, there are hardly any references or literature available in which the iron oxygen species which can be generated in water. Okay, because when we say we mimic the biology, some metal enzymes, etc. Many of the reactions or many of the metal enzymes, or when we consider human beings, us ourselves as the reservoir for solvent. The solvent is water. Okay, so our whatever reactions taking place is taking in place in the solvent water. Therefore, we thought that let us find out something in water. So in that context, what we did, so I did not prepare something new compounds. So some new already reported compounds in Professor Nam's group, I took it. For example, iron plus 2 and 4 pi ligand. And then what I did, I added water to that, something like 1:9 ratio water to acetonitrile. And then what I did, instead of oxidants like hydrogen peroxide, MCPP, or iodosyl benzene, what I did, I added cerium ammonium nitrate. That is Dr. Sankar morning said can. So when I did that, I added that, what I observed, I immediately observed the formation of an intermediate, that is iron peroxide species. So these iron peroxide species were already reported earlier by using some other oxidant. They were very well characterized earlier. But now I used water as an oxygen source, right, to generate iron peroxide species. And then this iron peroxide species was very much very much characterized by all techniques, USMRs and all those things, right? And so whether this oxygen is really coming from water, that also we check by taking H2O18. When we did that H2O18, so we could see the oxygen labeled oxygen here. Instead of O16 we got O18, so everything was confirmed. So then we wanted to check that, when we do this reaction, whether it is applicable in only one ligand, or whether it is applicable in when we take many ligands, because iron peroxide species were already reported by these ligands when I was working those days, right? Of course, they were not reported in water. So therefore, I thought I will try to generate iron peroxide species using water as an oxygen source, and the iron compounds are stabilized by different ligands. And fortunately, we observe that these are the ligands. These five ligands, all five ligands gives iron peroxide species in water. Okay, all these species were characterized by resonance Raman, ESI mass, EPR, and UV spectroscopy. Of course, we did some catalytic reactions and we got a very high turnover numbers for this product. Again, since this work was a bit novel, so we published that in Angvanti Chemie in 2009. So now that these two projects, what I just mentioned to you, these all both works were done during my postdoctoral studies. Now then I joined Goa University. So somewhere in 2008 I joined in Goa University. So this is what we are doing from then. So what we are doing is we are trying to prepare some heme and non-heme ligands in our laboratory, and then we try to prepare not only iron, we try to prepare many other metal compounds. Basically the first transition metal series and the second transition metal. So we do characterization by NMR and IR spectroscopy. Then we do metallation. Then we try to prepare the single crystals of this compound. Characterize, if not single crystals, characterize them by ESI mass. In single crystal, you characterize by them. A single crystal diffractometer. We have CHN analysis. We do that initially. We have CVDPV. We have a UVV IR, so no problem. EPR sometimes we send it to other places. So once we know that the purity of compounds is no compounds are very pure, we are convinced that the compound composition is known. So next step is what we try to see whether some intermediates are forming, and these intermediates, what we trace them by, as I said mentioned to you earlier, we trace them by simple UV visible spectra or spectroscopy, right? So we have this Agilent 8453 spectrophotometer, what we used to use earlier in my postdoc. So we have that along with the cyclic ultraviolet and other things. So we do initial characterization and then we try to stabilize the intermediate. Of course, because of limitations in infrastructure like cryostat, low temperature studies, etc., is not possible at the moment, right? So wherever possible, we send it outside, but we do some characterization studies. So at my laboratory, what we did, we have characterized some compounds which have formed at room temperature, and that is what some of the things I'm going to show you. And of course, finally, what we do is oxidation reactions we do, and then we characterize them by these particular techniques which are very popular in organic chemistry, right? So, and then we do some mechanistic study. So morning, I remember your Honorable Vice Chancellor was mentioning about the interdisciplinary studies, which will fetch you more kind of a results, which will or your publications, etc. In fact, this is nothing but the combination of all chemistry, all kinds of chemistry. So you can see here we do analytical chemistry, we do inorganic chemistry, we do organic chemistry, we do physical chemistry, right? So that is combination of all these things. So you can see here. So that's why we are able to publish in some good journals. So these are some of the ligands which we have prepared in our laboratory. Of course, some of them they are reported, but many of the compounds are not reported. So we are trying to explore the chemistry of the unknown compounds, right? So this red color one and this terpyridine and these things I have used during my postdoc. So therefore I have shown here. So rest of the ligands they are being used at Goa University laboratory. So Dr. Shankar in the morning he mentioned about manganese 4 oxo species, manganese 5 oxo species which we reported. So as you know that manganese 5 oxo species or manganese 5 oxo they're very popular as far as your photosynthesis and other things are concerned, right? So we don't have any infrastructure to characterize in this the compounds which we can prepare in the water, right? So basically when you prepare it in the organic solvents it becomes easier to characterize by mass and other most of the other techniques, but when you do something in water it's sometimes difficult, right? So of course I will just tell you how we characterized this particular compound. So this is what we did. So we prepared some TPPS compound, a porphyrin compound. This was prepared actually by our master student, project student, right? So then I asked him to prepare a manganese compound. So he prepared a manganese compound, and then this compound is this porphyrin compound is well known, and initially I mean some of the Chinese scientists had reported manganese 5 oxo, but there were no much evidences, no reactivity other thing. So we thought whether we thought let us do some reactivity and let us try to find out what is going on in aqueous medium. So in that sense what we did, we generated iron 4 oxo species in water because that compound is soluble in water, right? So we did that. So you can see here these are the spectra. Morning also Dr. Shankar showed you. So you can see here this is red color species is your initial compound manganese 3 compound which shows the Soret band at 466 nanometer, right? And on addition to PHIO, that is external oxidant, what happens is that, so you can see here this peak disappears, and what happens is that you get a new peak at 422. So so this 422 peaks you cannot get just like that. Even your iron manganese goes to some other oxidation state, or oxidation state, because we then tested whether it is +5 or +4. So very simple way to test, you have to test with something like simple the substrate like triphenyl phosphine or thionosil. When we did that, what happens was that, okay, so this because triphenyl phosphine it will take only, I mean only it will take oxygen, and if it takes, the reaction is quantitative, you should get iron manganese plus 3, final manganese plus 3, which you can trace by UV visible spectrum, and it should form quantitatively, that is 100% or 99% something like that it should form if the reaction is 100%. So we tested this triphenyl phosphine. So when we did that, actually what you can see a spectra. So 422 nanometers peak of manganese 5 oxo species on addition of the triphenyl phosphine. Okay, it went down like this, and then your iron manganese plus 3 species again come back to original absorbance. So based on that, and then we of course characterize the products formed by in the reactions triphenyl phosphine oxide, thiophenyl oxide, etc. We characterize them. We got quantitative yields of oxides, and based on that, we propose that this what species we got is manganese 5 oxo species. So now, since we are sure that it is a manganese 5 oxo species, we thought of doing some CH activation reaction. And then what we did, we selected this substrate, this substrate for CH activation reaction. So xanthine, dihydroanthracene, cyclohexadiene, fluorine, etc. And then besides that, we thought, because recently a lot of work being done by taking cyclohexene as a substrate. So cyclohexene is a very beautiful substrate which can undergo epoxidation reaction, as well as it can undergo what is called the CH activation reaction, right? To give a alcohol, the cyclohexanol, one hexene cyclohexanol, right? One hexene alcohol it can be. So since it was very fascinating, we also tested this cyclohexene and styrene as a substrate, and styrene is a popular substrate because it will give epoxide. So when we did that, what we observed in the CH activation reaction was that we got something like we got xanthine. We prepared corresponding deuterated xanthine, and we reacted with this manganese 5 oxo, and then we compared the Ki value of this. So when we got Ki value, something was around 8.5. So when you have 8.5, basically that is the first evidence which indicates the mechanism follows the radical mechanism, that is hydrogen atom abstraction mechanism. Then we to support this mechanism, what we did I mean we took a different substrate, found out their k2 values, that is the second order rate constants, and then we compared those values with their bond dissociation energies, that is the CH bond dissociation energies, because So those values are already already reported. So those values, BD values are known. They're taken directly from the literature. And then when we plotted against that, we got a linear plot, which again gives evidence that the mechanism follows the what you call the the hydrogen atom abstraction as a rate determining step. So based on these evidences, we propose this mechanism. So this was a mechanism proposed for this reaction, taking dihydroanthracene as this substrate. Then further, what we observed, so when we did the reaction with cyclohexane, so cyclohexane we took deuterated as well as hydrogen containing substrate. So when we did that, uh, we got a different sort of a reactant. The Ki value. So what was the Ki value? Ki value was 1. And when Ki value is 1, basically this is a straightforward evidence for epoxidation reaction to take place, right? So in other words, what we got, so here the hydrogen atom reaction did not take place in cyclohexane, although it is possible to take place, unlike the other metal oxide species. So to test that whether it is really going epoxidation, so we
ஏய்
tested.
ஆஸ்தி பண்ண முடிய மாதிரி செலவு ஆரம்பிட்ட கொடுக்குறேன்.
There is some disturbance, I think.
Okay.
Yeah, to test whether epoxidation is giving under, the quantity yields or no, we tested a styrene is the substrate. So when we did that, again styrene also gave a Ki value very close to 1, and you can see we almost got a quantitative yields, right? So when we use cyclohexane and styrene as the substrate. So this work was actually published recently in a new journal of chemistry with Dr. Shankar. And since the work was done, the same time when this work had come, so the Goa is no last year 2019 a new bridge was inaugurated, and the bridge is the third Mandavi bridge that is connecting that is connecting the main Panjim city to the other side of the city. So that is the third Mandavi bridge. The name is given as Atal Setu. Since we had used water as a solvent, so we dedicated this particular work because it was selected the front cover in New Journal of Chemistry. So fortunately, the journal people did not ask us any money or anything, so they gave a waiver for that, and then that came as a cover page. So that was that was a very good work in my opinion, when you don't have a lot of infrastructure, so one can start with a simple infrastructure what you have. So then again, after joining Goa Institute, we had long collaborations. Almost now 1 decade is over, more than 1 decade with the Professor Nam. And then, so I was with Professor Nam for some time. And then again, I thought I will come back to ruthenium species. So in 2013, somewhere, what was going on in the area of this biomimetic chemistry was that whether in cytochrome P450, the proposed mechanism says that when the organic substrate, especially the alkanes reacts, you get a quantitative yields 90% or 80% yields of alcohols, etc. Right? And therefore, based on several evidences, what mechanism was proposed? The mechanism proposed was something called as a rebound mechanism. Okay, so what is a rebound mechanism? So if you look at this particular A mechanism here, so you have here some oxygen, metal oxygen species. So what happens? The hydrogen is abstracted, and then what happens? Hydrogen is abstracted, so it remains here. You have something radical, and then you have OH minus. Okay, so what happens is that once hydrogen is abstracted, so hydrogen goes with this your oxygen, so it becomes manganese metal plus 3, and then this becomes radical. So in cytochrome P450 or in the case of heme system, what is reported is that, so this this particular species immediately in the it rebound back to your oxygen, that is a hydroxyl species, and then finally it gives the oxygenated product, and it gives from +4 it goes to +2 oxidation state. So that is the product they give, and therefore the yields are a quantitative yield. But recently, what was observed, when many of the similar reactions were carried out with non-heme systems, what was observed, the products were never 100%, or they were never close to 100%, like 80% or 90%. The yields were never. But unlike in porphyrin systems or heme system, the products are very close to 80%, 90% like that. So what was the reason for that? was actually studied, investigated by Professor Nam's group with lot of metal oxo species. They did with iron oxo species, they did with manganese oxo species, they did with chromium oxo species, and they explored all those possibilities. And then they noticed that unlike the heme system, what is the mechanism going on in non-heme system is a non-rebound mechanism. The mechanism is going is a non-rebound mechanism, and in non-rebound mechanism, what happens, this radical actually what happens, it escapes from the cage. So this is a cage, this radical escapes from the cage, right? And then I mean it goes it can be trapped actually by substrate like tetra what is called as a bromo trichloromethane. So like that some substrate can be used, and then that can be trapped, right? It escapes and finally it gives the hydroxylary product. And of course the metal plus 4 oxidation goes to metal plus 3 oxidation state, and that is the reason the yields are low. So based on this background, we thought of, now let us see, lot of things are already reported, so why to do again with the iron? So we thought of doing with ruthenium oxo species. And ruthenium oxo species, again I don't want to prepare ruthenium TMC compound, so I thought of doing something else. So I took a TJ Mayer's compound, that is he prepared a very nice compound, that is he prepared uh, he prepared a terpidine and bipyrimidine compound of ruthenium 2, and he used or he exploited like anything for many of the water oxidation reactions. Okay, so water oxidation reactions were reported, and in fact they also traced, they did not give a clear cut evidences for ruthenium 4 oxo with this ligand, but that we have shown in our study, right? So you can see so we prepared we generated ruthenium 4 oxo species. So this initially 485 peak is ruthenium 2 species, and in astronitrile, and on addition of a PHIO, this absorbance of this peaks decreases and it goes to something like 445 nanometers. There is a shift in the nanometers also, right? Absorbance decreases. So now when we added this, it happens like this. So we thought we will characterize this, and when we characterize this, we found that it is actually a ruthenium 4 oxygen species, and that was very well characterized by ESI mass. You can see here O18 labeling studies, H2O18 labeling studies, all those things were done. And then we also did with resonance Raman studies. So it was proved that the ruthenium is bonded to ruthenium oxygen, right, by this particular characterization method. And then we thought of doing the reactivity. So on addition of a substrate like for example here ethyl benzene, so what happens, ethyl benzene, so the again it goes back to this red color spectrum goes back to something else, and it gives a nice your first order zero no first order zero first order kinetics. And based on that we also found out the second order rate constant. So this is a reaction on addition of a ethyl benzene. And then we compared with deuterated substrates. So when we did that, we got a large KI, okay, like other iron compounds, etc. Okay, and then we again we suggested the mechanism is your hydrogen atom abstraction mechanism as a rate determining state, and this was again substrated by taking a bond distance energy, CH bond distance energy versus your log K2 values plot, right? So this was done, and of course this work is already published in the JAX 2015. Then we thought again, like in my manganese compound, I thought I will do it with cyclohexene, or we do it with cyclohexene. And as I said to you, just 1 second. So we thought of doing with cyclohexene. So when we did cyclohexene, interestingly, you will notice that a cyclohexene again we got a different Ki. It is not a Ki is equal to 1, but we got Ki is more than something shown here. So now based on this Ki, one can straightforward say that this epoxidation is not taking place here, right? So we again did the same reactions with same reactions, product analysis, everything we did, and then finally come to the conclusion that cyclohexane one alcohol is forming as a product and no epoxidation is forming. So now to test that it is not happening, we also tested with styrene. Styrene gives only epoxide. and triphenyl phosphine also gives only epoxide. So therefore, oxygen transfer is possible, but it is not happening with cyclohexane. So this, of course, this work was also supported by DFT calculations, and then therefore it was published in JAX 2015. So therefore, I must thank that I learned something new during this particular era. Again, on non-heme systems related to non-rebound mechanism. That's more important. So there's something a new concept. So again, we did with some iron compounds. So iron compounds also we did. Iron compounds again, you can see a very large, or very big number. Ki is equal to 66, right? Ki is one of the paper where you will see this number very high, right? So this all product analysis were done by GCMA. So oxygen labeled is or not, it is also done. So you can see oxygen is coming from the iron 4 oxygen species. So 70 becomes 72. So all those things was done, and you can see here the products were quite high in the case of the cyclohexane, but for some epoxide also obtained when we did a catalytic reaction. So of course, lot of things have been supported by DFT calculations, and this work actually we submitted initially to Angevante. It got rejected. Then we submitted to chemical science. Then also it got rejected. Finally, it was submitted to JPCL. So this was work. This is very recent work. What we did with, of course, it was done in Professor Nam's lab, but initial the work partly I contributed. So I thought I will share with you. We did a very interesting work here. So what was the work? This is a manganese Carol system. So manganese Carol, manganese plus 3 is was able to form a peroxo species as well as the oxo species in the same reaction. That was something interesting. Okay, so that was something interesting. Therefore, no, you can see here. Therefore, it got published in your JAX in 2017. So manganese carol species in the presence of oxygen and a radical, it forms a your manganese 4 peroxo species. Okay, of course, in hydrogen peroxide and base also it forms peroxo species, right? And then in the presence of a PHIO, it forms manganese 5 oxo species. So this manganese 5 oxo species again can be converted into a peroxo species, right? In the presence of a base, and these steps can be done several times, and therefore it is a reversible steps, right? So this particular initially these things were observed by doing a simple kinetic, U visible spectroscopy. So you can see here this red color is starting compound. Somewhere 478 is shown. Red color is starting compound. So on addition of a PHIO, what happens? All the peaks, this there is a peak shift for 347 and 407. The new peaks are formed, and that is because of the oxo. Okay, that is because of the oxo species, right? And then one can again, one can prepare the peroxo species by just putting the base. So once base is put, it goes to your the new species. This was well characterized by your Raman and other studies. There was no absolutely doubt about it. And then we did other reactivity studies also. Now coming from some, some work done in the NAMS lab, very in this thing. So again, I am coming back to the work done in our laboratory. So very recently, we prepared pentadentate non-heme ligand. You can see here, which is similar to your N4PY. Okay, and then this ligand was prepared by a simple reaction. So you can take something like a diene, and then you just condense with the pyridine carboxyaldehyde, reflux it, and then you get this. Then you do hydrogenation and methylate it. So this ligand was prepared, and then we thought of doing the manganese compound of it. So we prepared manganese compound. So you can see your manganese compound was prepared. So of course we prepared here the cobalt and nickel compounds also. Therefore numbers 1, 2, 3 are given. So I am going to the manganese first compound. So in addition to, like for example in earlier cases, as I mentioned to, we worked on oxo species. We also work on the peroxo species. So interestingly, this manganese compound was not forming oxo species. So therefore, we thought of doing peroxo intermediate in our laboratory. And you can see here, so this was a manganese plus 2 compound on addition of hydrogen peroxide, something like 10 equivalent and triethylamine in estronitrile. So you can see this A species, A starting compound changed to a very purple, I mean almost a bluish color species intermediate in solution. And you can see this is the spectra. These are the spectra on addition of the hydrogen peroxide. So it was quite stable. The species is also characterized by ESI mass and all, EPR, etc. Okay, and then we also got some DFT calculations done by my colleague from Central University of Haryana. So he showed that this whatever solution we have and the manganese peroxide species we propose, DFT shows that it is a side-on species. Then we did some reactivity with this. So we did reactivity is something like a 2 PPA, 2 propionaldehyde, and also CCA. But CCA was very fast reacting, so we thought of doing only reactivity with this. So there are some reports by Professor Shastri and also Professor Nam saying that the reactivity of manganese peroxide is going via the electrophilic step or electrophilic pathway. So we thought of doing that here also. We thought whether our reaction is a nucleophilic or electrophilic. So we tried reaction with the deuterated substrate. When we did that, we got a Ki value between the deuterated substrate and the normal substrate something like 1.7. Okay, so of course we need to do some more reactions over here, and we check whether really it is 1.7. Some more experiments on that to be done. Of course, this work is we submitted to Dalton Transactions, and it is actually come for revision. So that's why I said some of the work are to be incorporated in the revision. So similar to that, we also prepared some tetradentate ligand, and we prepared this time a cobalt compound, and we thought we will try some peroxide intermediate. So on addition of, so you can see this is a tetradentate ligand, something like a trans-cyclohexane you have, and then quinoline ligand based moiety you have. So we prepared a cobalt compound. We characterized this compound by USI mass. We have a crystal structure also. There is no problem. We have prepared a crystal structure of starting compound, and then we again tried to do some tracing of intermediate. We could get a peroxide intermediate, not other intermediate. So we can see here. So this is a starting spectrum, and on addition of hydrogen peroxide, you will get this spectrum around 520 nanometers. This compound is characterized by ESI mass. We also did O18 studies, so absolutely there is no problem. Some more work is being under investigation. We are doing the reactivity studies again, similar kind of things we are doing with cobalt, what we have done with manganese. Interestingly, this time the Ki value is very low, so this indicates the reactivity what is reported earlier by Sunam and Shastri group. They said electrophilic reacted, probably in this case it is nucleophilic, as reported in previous literature. So this big work we have not submitted yet. In addition to that, we are doing a lot of other catalytic reactions. So some of the things are being reported already in 2015 inorganic chemical. So we do simple things like IR spectroscopy, UV, CV, and then some ESI mass, and we try to find out a structure. So we have done this particular work with alkanes again. So we did SAGE activation reactions with nickel compounds, right? And lot of literature is also available. So we got these products, this hydroxylated product along with the ketones. We of course the ketones are the minor products. Then we did again the nickel chemistry with other ligands, cyclohexene ligand. So interestingly, you can see we have done this hydrogen, this R group we have replaced with a methyl group as well as the H groups, and we have done the catalytic reaction. Okay, so in this again, this compounds we characterize by structure and this CB, and then some intermediates was obtained. However, we could not give a clear-cut evidence for that. Of course, we did some catalytic reactions with the alkanes. We got this data published in Inorganic Chemical Extra in 2019, and also Journal of Structural Chemistry. So then we again we thought again we will prepare some more compounds. So what we did with cobalt, so we prepared a cobalt wherein you have here H groups, NH groups you have instead of N methylated groups. So again we did some studies with that. I mean not cobalt, copper. So compounds were studied by this one EPR, and then structures were already reported. Unfortunately, we could not do. I mean, we could not get any data on CH activation or any other organic reactions. So we thought of doing some other biological studies. So we did some microbial study, and these results, in fact, were published recently in the inorganic chemistry. The interesting thing is also we noticed that your when you prepare a starting compound, so we noticed that this particular goes by cis fashion. So this since the astronitriles are here, so they can be replaced by ligands like bipyridine and phenantholene, so to give you altogether new compounds. So these compounds were generated by us, I mean prepared by us, and the structures are reported. So this is a pentadentate ligand. What I showed you with the manganese. So we prepared cobalt compounds, your cobalt, copper, and this thing, nickel compounds, characterized by them with ESI initially, IR spectroscopy, UV spectra. Okay, the powder pattern, all those things, cyclic voltammetry, everything was done with them, very well characterized, right? And then this work was also done. By changing the counter anion, so that is perchloride was changed with the tetraphenyl borate, and we could get actually by using tetraphenyl borate we could get quite good yields of hydroxylated products, right? So by changing counter anion also was important, and this work was published in 2017 in ICA. Very recently in 2020 we thought, I mean, let us do something else. So this work was done in collaboration with my friend Dr. Anil. Okay, Dr. Anil and professor scientist from ISCT, Dr. Giri Babu. So we thought we will try to do this, I mean try to test this particular compound in water oxidation. So when we did that manganese compound, so you see here, so we have this manganese all characterization was very well done. So we thought of doing this particular thing. So you can see here the onset potentials in different pHs were different. So we could plot, and from Topel plot and other data we could propose this mechanism for auto oxidation, right? So after the after before water oxidation and after auto oxidations, the 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 what you call the whether the manganese compound exists in solution or not, that was checked by your XPS data. Okay, and this work was recently published in
கதை கதை
Sustainable
பண்ணலாம்
Agriculture
போய் சொல்லாதீங்க.
Tools. In addition to your water oxidation, we also did some epoxidation reactions. So this work is been going on, and hopefully we are doing some more reactions with other substances also. So hopefully we'll be able to complete very soon. Yeah, so I'm just taking another 5 minutes, probably 5 to 5 minutes more. So again, we did not leave ruthenium dioxide species we prepared earlier. So we thought we will try something else with ruthenium dioxide. So you can see this is the ligand. So the structure we reported, and then we published in Dalton transaction 2015. So you can see two oxygens are trans, characterized by I mean UV visible spectra and then mass, right? And then we did reactions with the acridine substrates as well as the other means alkyl hydrocarbons. So in acridine substrate, the mechanism was the hydride transfer mechanism is shown here. And for your hydrogen atom abstraction substrate, we chose this, and the mechanism was hydrogen atom abstraction as a rate determining step, and so mechanism is shown here. So some steps also we showed by cyclic voltammetry. You can see a very clean and neat spectra over here. So this indicates that reaction is taking place, so there is absolutely no problem. Of course, only thing is final characterization. So this work actually be published. Some more work is so now we have that ruthenium 6 dioxo. So we thought whether ruthenium 5 oxo can be prepared. Ruthenium 5 oxo, but 5 oxo our efforts were not successful. In fact, we were able to prepare ruthenium 5 dioxo intermediate. So what we did was very simple. We had ruthenium 6 dioxo intermediate. So we thought we will try to use, we will try to use electron donors. So we thought we will try to use ferrocene's derivatives. So when we use ferrocene derivatives, we were able to get ruthenium 6 to ruthenium 5 dioxo species. When we did that, so you can see here when we did that, this is ruthenium 6 dioxide intermediate 388 nanometers. On addition of ferrocene or 2,2-dimethyl ferrocene, so what happens is that somewhere around 438, again you get a vibronic peak, and this peak 750 peak is nothing but the ferrocenium ion. This after giving the electron, so it forms a ferrocenium ion. So that peak corresponds to that. So this compound was very well characterized. It again gives vibronic spectra. You can see here the mass and everything was very clear. So there was no problem. So we also characterized this compound by EPR. So it was showing the the ruthenium 5 oxo, 5 character, EPR character, which was similar to what is reported earlier. But some more work is to be done. It is not so clean. So I cannot at this moment say that it is 100% the 5 oxo species. So since that was an intermediate, we did some CH activation reactions. So results you can see here. So that intermediate was reacting very nicely. You can see here for a 38 band decreases with a pseudo first order rate constant. And then we could do that for xanthine like earlier cases. So we got a large Ki value, and then we also did with other substrates. So these are the Ki second order rate constant for them, right? And then we plotted a bond dissociation energy with the log K2 values. We got this. So this suggests that the hydrogen atom extraction is a rate determining step in this case. So this was this was the proper proposed yields for this reaction. So I propose this work is not published as, but we propose that ruthenium 4 oxo species is forming in these reactions with axial ligand OH, and therefore there is no further reactivity. OH is a more nucleophilic, and for this we also have evidence with the mass, so there is no problem. Mass and APR is there. So when you compare the reactivity of ruthenium 5 oxo species with ruthenium 6 dioxo species, so what we notice is that, okay, so you can see here ruthenium, this is a reactivity of ruthenium I compared with ruthenium 5, ruthenium 6 and ruthenium 4 species. So what we notice is that ruthenium 5 species with xanthine reacts very fast. Okay, so when we compare ruthenium 5 to ruthenium 6, the reactivity is 10 times. When we compare ruthenium 5 to ruthenium 4, the reactivity is something like 200 times. Okay, and when we compare ruthenium 6 to ruthenium 4, it is something like 21 times. So that this work is not yet being published. So hopefully we are going to publish it. So now since we have prepared lot of ligands, since we have prepared lot of non-heme ligands, so we thought of let us try these ligands, and those are quinoline based ligands. We thought of doing something like no, what you call the quenching of a what you call the quenching of a organic compounds which are being used in a terrorism and all those things, like for example trinitrophenols. Okay, so when we did that, we actually got a good results. You can see here. So this is your starting compounds, right? So this is my starting compound ligand, and this is after adding of trinitrophenol. So you can see the fluorescence. These are fluorescence compounds. So this fluorescence is quenched after adding a triphenol. This thing. So this indicates that there is no this triphenol compounds can be easily quenched. So these are your the intensities you can see here. So last one, so the first one is orthonitrophenol, metanitrophenol, paranitrophenol, 2,4-dinitrophenol, and the last one is trinitrophenol. So these four, 5 compounds, the reactivity is not so good, but TNP is reacting so nicely, right? And therefore we thought that that is a this our ligands are much more better to quench this. The TNP. So finally, what we got, interestingly, for this what you call brown color solution, yellowish color solution, we crystallize it, and we got a crystal structure of it, right? And we, because most of the time what they in reports they say that there's a resonant electron transfer mechanism taking place, but in this case we ruled out that the resonance electron transfer mechanism is not taking place. In fact, the quenching takes place at the ground state, because directly the adduct is forming, and the adduct was characterized by single crystal study, right? So in addition to other things, we are also doing some more work. So what you can see here, so we have prepared so many ligands, we are trying to do some work. So you can see we have prepared one copper compound with this ligand. Okay, this is a crystal structure we have. This is BQEN we call, but NHNH, it's ethylene diamine. But now instead of CH2 we have inserted one more methylene group, and we have this thing. So when we do this and then we prepare a compound, you can see what happens. So the structure of this compound is very close to a square pyramidal, but the moment we put one hydrogen CH2 group here, right, the structure deviates almost 46% from square pyramidal. right? So we are trying to prepare other ligands also. Hopefully, we are going to get some exciting results, and then we can publish in some good journal. In addition to, I'm not going to discuss more about this. In addition to that, I've just little bit from last 2 years, I've just started some other area of research. So we are doing some structural chemistry of metal carboxylates, because metal carboxylates gives very interesting chemistry, what we call a coordination polymers and MOPs. So we are not expert in that area, but we have just started this area, and hopefully over the period of time we are going to get some good results. So this work yesterday only. So this work already published IUCR Crystal journal. This we did with the cobalt compounds. Okay, this is already. I did not change it. The Journal of Indian Journal of Chemistry. It is already published. The page numbers are come. I did not update here. Okay, then we have also published. Recently submitted a paper in Chemistry Select. So for this, yesterday only the minor revision has come. So there is no problem. Then this we are trying. So we are trying hydrothermal versus solvothermal methods. So in fact, what we did, we did some reactions with cobalt nitrate and cobalt acetate. You can see here. So this is our cobalt source, cobalt 2 we took, and then we took something like nitroisothalic acid, and then this one. So when we did that, in fact, the reactants are only. The only reactants are only three. Okay, but we got five products. We got five products in one of the reactions. So here these five products we got we using succinate, and then we are doing some other studies, like somebody said, no, the gas adsorption. We are doing that. Of course, we have not completed this work. So we have these studies in addition to what we have done with metal oxygen intermediate. So some more work we are doing with copper, cobalt, all those things we are doing it. Of course, we are using hydrothermal synthesis, because we have autoclaves here, we have a oven here, and we are trying to develop infrastructure for this particular purpose, right? And then our students are being well trained on this single crystal diffractometer. So they are being trained to solve the structures by themselves. They are being trained to mount the structures by themselves. So absolutely, we are giving some good training to them. So this is all about my work in collaboration with what I did with Professor Nam and my other collaborators like Dr. Shankar, Dr. Anil. Yeah. So I finally acknowledge the my School of Chemical Sciences, Goa University, DSP, UGC, CSIR, and KRF for funding. And then I think I have been awarded one PhD. One student is already awarded PhD. My five students are doing PhD, and I have around 35 students already guided your dissertation students, right? So they also helped me a lot. Okay, so I thank my all collaborators, Professor Onwunam, Professor B.R. Srinivasan, one of my boss, my PhD guide. So he is now senior professor here. Professor Sunichi Fukuzumi, Professor A. Bucha, Dr. Giri Babu, Dr. Shankar Lingam, Anil Kumar Vardhan, Dr. Mariappan, Dr. Sandeep Day, Professor Iron Furtado. Yeah. So this is the end. Thank you very much for listening in without any problem. Yeah, thank you, doctor. I'm
Well,
done with.
okay. Now the session is open for discussion. Yamuna, if you receive any questions from audience, you just ask to professor.
Okay, sir. Sir, the past participants have posted few questions, sir.
Yeah.
Question number 1. What kind of intermediate you observe for nickel systems and what is the oxidant used?
Okay, so for nickel case, actually, what we did, nickel, we use a MCPPA. Okay, we use MCPPA as oxidant, right? And with MCPPA and nickel, there are, nickel 4 nickel 3 oxygen radical species is reported, right? So we did not get any evidence for that, but based on our product analysis, organic product analysis, we have proposed the mechanism saying that in our solution, what is generated after adding MCPA is nickel 3 oxyradical.
So, the second
So,
question is,
yeah.
could you comment on the reason for the effect of counter anion in product yield?
This probably we need to do more. More. We have to check actually more counter anions. We have just checked the two counter anions, that is perchlorate and tetraphenyl borate. So in fact, we are doing some studies on that to understand what is exactly the effect of counter anions. We have not done that. We have not even cited any explanation or justification for this effect in our paper.
Sir, and the final question is, did you ever observe monooxoruthenium, and if so, whether mono or dioxo is acting as strong oxidant?
In which case, I mean, where you said?
They haven't mentioned the slide, sir.
Because monoxo species already I showed in first few slides. No, the already reported, very well reported. So with the cyclum ligand, tetramethyl cyclum ligand, oxygen ruthenium 4-oxo species is very stable. One can obtain the crystal structures. I mean the single crystals. The structures of ruthenium 4-oxo is not so. I mean, only thing is a difficulty is what the synthesis of those ruthenium compounds. So the yields of final products, the ruthenium oxo species you get, they are very less yield. But they are very stable. That is only a difficulty. Otherwise, ruthenium, most of the ruthenium 4-oxo species are very stable at room temperature. So whatever we studied, we reported that is ruthenium 4-oxo species, and they are characterized by various advanced techniques. There is no problem. So now probably the question you are asking, that is the question, last question, based on last 1-2 slide. I mean, I was talking about ruthenium 6 dioxo and then going from ruthenium 6 to 5. So probably the question is related to that. So there also, I mean, from ruthenium 6 dioxo, when you put triphenylphosphine, you take ruthenium 6 dioxo and add triphenylphosphine or thionyl. So moment you add that, the compound what you are getting is a 2 electron reduction compound or 2 electron oxidation compound. So what happens? The triphenylphosphine becomes triphenylphosphine oxide, and ruthenium 6 become ruthenium 4, and that is nothing but the ruthenium 4 oxo. So that chemistry is already known. Nothing new in that.
And one participant have asked the question, sir. Sir, in slide number 17, you mentioned about NAM work. Is it by instrumentation physically or any software work like Gaussian?
Which one?
Slide number 17, sir.
Uh-huh.
You have mentioned about NAM work. Is it instrumentation physically or any software work like Gaussian?
17th slide. You said some 17th slide. Let me check it. What is the 17th slide? Okay. So what you ask about? You want to say that the DFT calculations?
Yes, sir.
Yeah,
They mentioned only the slide number.
Yeah, DFT calculations. I think he is talking about the DFT calculations, right? So that actually, I mean, I will send the paper to that. I mean, who is asking that question? I will send the paper, so there is no problem. He can go through it. So of course, this is all done by not Gaussian. It was done by other software. Huh?
Okay, sir.
Yeah, I don't remember that, but it is done by other software. It was done by a big, I mean, the DFT theoretical chemist, the Professor Sesson Sheikh.
Okay, sir.
Yeah, in Israel. Yeah.
That's all, sir. Thank you, sir.
Yeah. Any more questions?
No, sir.
Okay. Fine. In the absence of any other question, we are very happy about Dr. Sundar Duri's presentation and the way that he interacted with the participants and answering the questions. And it is very nice. It was very nice presentation, Professor. Thank you very much for being with us and sharing your enlightening knowledge to us. Thank you very much.
Yeah. Thank you very much, Dr. Mohan. Yeah, it was. I mean, it was indeed a very good opportunity for me.
Actually, right. Dr. Sundar, I am Prabhakaran. I am not Dr. Mohan. I am Dr. Prabhakaran. Actually, the system is already with Professor Mohan. Hence, it seems Mohan.
Okay. I'm very sorry because initially I did not keep a. I mean, I did not.
It's okay, no problem. Absolutely.
Thank you, Dr. Prabhakaran.
Thank you.
Yeah, sure.
Thanks.
Yeah, thanks.
Thank you, Doctor. Thank you so much for your nice presentation. Yeah. I also thank Dr. Prabhakaran for sharing the session, morning session as well as the afternoon session. Thank you so much, sir.
Thank you. Welcome.
Yeah.
Thank you.
Dear participants, tomorrow morning the sessions will commence from 10 a.m. So try to enter the meeting around 9:45. So only those who are watching the sessions and filling the feedback form, they will receive the certificates. This is for your kind information. Thank you so much.